So, hello everyone. Today I am going to start the next topic, that is measurement of oxygen mass transfer coefficient KLA. So, in the last lecture we discussed about mass transfer coefficient KLA and what are the different methods to experimentally determine the KLA, that we will be discussing in today's lecture. But in addition, there are also different correlations are also available to estimate the KLA, that we will be discussing in the next lecture. So, if you remember, in the last lecture we discussed aeration and what are the different steps involved in the, particularly in the transfer of oxygen from the air bubble to the cell. So, we discussed there are 8 steps. However, the liquid film was found to impose the major mass transfer resistance, and further we discuss what are the different factors which affect the oxygen transfer. Now, today we are going to discuss these 3 experimental methods to estimate KLA value. The first one is oxygen balance method, followed by dynamic method, then sulfite oxidation method. Before we go ahead with these methods, first let us quickly revisit how we measure dissolved oxygen. Of course, this topic will also be part of the instrumentation and control, but here we will briefly discuss that how dissolved oxygen is measured. So, there are 3 main methods: the tubing methods, use of mass spectrometer probe, and third one is the electrochemical detector. So, electrochemical detector are the most common one for in situ monitoring of dissolved oxygen, and there are 2 modes that it operates, that is galvanic and polarographic. You can see this is a galvanic and this is a polarographic. So, here we do not need to supply the voltage and current is measured. In case of polarographic, a constant voltage is supplied and then finally current is measured, and you can just see in the anode electron is generated in the both the cases, and the cathode it is utilized. And overall reaction I have mentioned here, this let us say this is a, at the anode Pb is converted to Pb plus plus and 2 electron minus, and at the cathode this water, oxygen and 4 electrons are combining to form 4 OH minus, and overall if you just see there will be 2 Pb plus oxygen plus 2 H2O, it will be 2 PbOH. Similarly, here also at the anode Ag is combining with Cl minus, it becomes AgCl, 1 electron is released, and at the cathode this water is combining with electron and oxygen, it becomes H2O2, and H2O2 further combines with electron to form the OH minus. So, this is the overall reaction. So, in this case you just see in the both the cases you can see this Teflon membrane or membrane. So, this is the first thing, how oxygen permeates to this electrochemical detector. So, there is a semi permeable membrane that affect the time response for the sensor. You just see the first one is oxygen permeable membranes, this separates fermentation fluids from electrode. Then oxygen diffuses through membrane to cathode, oxygen is going to the cathode where this reaction is taking place, and reaction produces a current proportional to oxygen partial pressure, means how much oxygen has been utilized, and there is a electrolyte solution that need to be replenished periodically. Now, how it happens? Oxygen moves from bulk liquid, then followed by the liquid film at the membrane surface, then it passes through membrane, then it goes to electrolyte, then finally it reaches to cathode where oxygen is utilized. And mostly this diffusion dominates inside the membrane or electrolyte, and as I told, depending on the membrane type and its thickness, it can cause a slow response. A typical the response time, if you just see steam sterilizable probe, the response time is quite quick, 10 to 100 seconds, and the measured as time reaches to 63% of total change after a sudden shift in oxygen level. So, we have to see depending on the change in the oxygen concentration how quickly it is able to measure the concentration, and further as this is controlled by mass transfer. So, if we are able to have a good mixing which can reduce the liquid film thickness, we can get a faster response. In addition, there are microprobes, they are smaller cathodes, so they require low oxygen and it is expected to get a faster response. And this can be used in even unagitated system where proper steering is not there. And for online monitoring, particularly for in situ, the stream sterilizable probes are inserted directly into the bioreactor. So, here are few other important points. This calibration, so this requires a frequent calibrations, and there are challenges like membrane fouling by cells, noise from the air bubble as well as some signal drift. And how it measures, as I told, it is measuring the oxygen partial pressure, not directly the concentration, and partial pressure is further converted to the concentration. Need oxygen solubility data at a given temperature and pressure for the conversion. Other option is one can follow this gas law, it says PV equals N or T. Now, there are three different methods to measure a KLa experimentally. As I discussed initially, oxygen balance method, dynamic method and sulfite oxidation methods. So, we will be discussing one after other. So, first is oxygen balance method. As the name suggests, what we are going to do, we are going to calculate the oxygen transfer based on the mass balance of oxygen in the gas and liquid phases. So, basically what happens here, we have to measure the inlet and oxygen concentration in the gas phase, because we are continuously supplying the, if this is a bioreactor, you are continuously supplying the oxygen, and here you have to measure the, this is the inlet, this is the outlet, you have to measure inlet and outlet oxygen concentration. Then you can determine the oxygen uptake by the liquid phase. What is the difference between these two? And once it is done, then we apply the mass balance equation to estimate the KLa value. So, as you can see here, it is very useful and can be applied to the continuous systems, and this measurement of concentration at the inlet and outlet, we require very accurate measurement to determine the KLa value. So, here we are just measuring at a single point, and this method is applicable during normal fermentation operations, because there is always, particularly in aerobic fermentation, the supply of oxygen, and accuracy for this method highly depends on the precise measurement of inlet and outlet gas composition, flow rate, pressure and temperature. So, let us say first we will see the mass balance based on the concentration. So, what will be the rate? what is the inlet and what is the outlet, because there is a, as of now we are assuming there is no utilization and no generation. So, it will be 1 upon V liquid volume minus flow rate into concentration at inlet minus gas flow rate and concentration CAG at outlet. So, this is the rate of oxygen transfer. Now, here it is important that this flow rate at inlet and outlet may vary, it need not be same, and further as it is difficult to directly measure the oxygen concentration, mostly oxygen is measured in terms of partial pressure. So, what we are going to do, we are going to apply PV equals N RT, or you can say P equals CRT. So, C will be replaced by P upon RT. So, you just see CAG will be replaced by PAG upon R is common TI, and similarly this CAG will be replaced by PAG upon T outlet. So, concentration is replaced by P upon RT. So, here there will be inlet temperature, there will be outlet temperature, this inlet flow rate, outlet flow rate, inlet pressure, outlet pressure, volume is constant and R is constant here, gas constant. So, in this way, by doing simple oxygen balance method, we are able to calculate the value of Na. And once the Na is known, then how do we calculate Na as KLA CL star minus CL. So, once Na is known, we can measure the CL value and then we calculate the mass transfer coefficient. And further, this KLA depends on the exterior speed, air flow and breath properties. So, when we are applying this method, we are assuming the liquid phase is well mixed, gas phase is well mixed, and we are assuming the constant operating pressure throughout the vessel. Now, next method is dynamic gassing out method. So, in this method we measure the oxygen transfer by observing dissolved oxygen recovery after deoxygenation. Now, there are different techniques to do deoxygenation. One option is you purge the nitrogen gas. Other option is if there is live biomass, you stop the aeration, automatically oxygen level will go down. So, what you have to do? You have to first deoxygenate the liquid using, let us say, nitrogen spurging, and once it has reached, say this is the DO concentration, this is there, all of a sudden I started purging, let us say, nitrogen, it will come down like this. Then once it has come to certain level, again you start passing the oxygen, it will recover like this. Then introduce air and monitor the dissolved oxygen to increase over time, and use dissolved oxygen versus time data to calculate KLA using exponential fitting, because this recovery is a exponential graph. So, this method is simple and widely used, and it requires a accurate dissolved oxygen sensor, because you are going to measure the dissolved oxygen at a given time intervals. So, what is happening here? We are measuring the dissolved oxygen after a step change in the aeration. So, basically it is becoming kind of a unsteady state mass balance, because we are disturbing the steady state, and here it requires low cost analytical equipment, and further it is independent of oxygen solubility. CAL value is not required, and this method can be applied even for a small bioreactor, particularly at the lab scale. So, here again there are some assumptions like liquid phase is well mixed, DO probe response time is less than the 1 upon KLA, and high stirrer speed to remove liquid boundary at the probe, because the probe is solid. So, there may be formation of this liquid boundary layer or liquid film at the probe also, and this we are neglecting the gas phase dynamics, and this method is valid for small, this rigorously agitated and low viscosity systems. So, it also requires the low gas hold up, high gas throughputs, and even for the little gas recirculation. So, in this method, as I discussed initially, this is the time and this is the concentration CAL. What is happening here? It is at the steady state. Maintain steady dissolved oxygen in a stirred aerated broth. Stirred aerated broth. Then you have to deoxygenate. So, stop the air. You stop the air, and if there is a biomass, it will automatically start utilizing the oxygen, or you purge the nitrogen gas. So, here we have stopped the air and started, let us say, nitrogen. It will come to a certain low level value of oxygen. Then from here again you restart the aeration. So, here the aeration is started again at a constant flow rate till it reaches to steady state value, that is the CAL bar. So, for the steady state concentration of, we are writing CAL bar here, and keep the dissolved oxygen above this critical concentration to avoid affecting the cell respiration rate, particularly if you are using the system with biomass. Now, as this is unsteady state, so this will be dCAL upon dt equals KLA, the transfer rate, KLA CL star minus CL minus utilization rate Q naught into X. Now, what happened at the steady state? At the steady state, we have started the aeration again. It is reaching to a saturation concentration of C bar. So, if you assume it is reaching to the steady state, so at least then rate of accumulation will be 0, and then Q naught X, this will be equals to KLA CL star minus CL bar, because this is what it is reaching up to this concentration. Now, if I put this value of Q naught X over here, so what I am going to get here, in, let us say this is equation 1, this is equation 2, I put the value of Q naught X over here. So, I will be ending up with KLA CL star minus CL star minus plus CL bar. So, CL star will be cancelled out. So, we do not require the CL star value for this method. This is what I discussed earlier. So, it turns out to be, it becomes KLA CL bar minus CL. and when we integrate it, so this will be dCl. So if I want to integrate it, it will be dCl upon Cl bar minus Cl equals KLA into dt. So you can integrate this. So this will be ln, and what is the limit we are taking? You can take any 2 points, let us say time t1 to t2, and for t1 the corresponding value is the CaL1, and for t2 the corresponding concentration is CaL2. So this will be ln C bar minus CaL1 minus ln CaL bar minus CaL2 divided by delta t. So in this way we calculate the KLa value using this guessing out methods or dynamic guessing out methods. So here you can just see this, once you are having this data T2 minus T1 and you are having x axis is ln Cl star minus Cl1 divided by Cl1 correspond to time T1, then Cl bar minus Cl2 correspond to time T2 divided by delta t. This will be T2 minus T1. So in this way we calculate or get the KLa value. So this is quite simple method and quite commonly used in the laboratory scale as well as at the industrial scale to measure the KLa value. So we have to quickly deoxygenate, bring down the oxygen level down, then further you start the aeration and measure the concentration of oxygen at any 2 time points T1 and T2, and you apply this expression, you will get the KLa value. So what is not required here is, for this method the Cl star value is not required. So I have listed one example here. A stirred fermenter is used to culture hematopoietic cells isolated from umbilical cord blood. The liquid volume is 15 liter. The simple dynamic method is used to determine KLa. Air flow rate is shut off for few minutes. It means we are deoxygenating here, and dissolved oxygen concentration drop. Air supply is then reconnected at a flow rate of, at a constant flow rate of 0.25 liter per second. Following results were obtained at a stirrer speed of 50 rpm. So at any 2 points, let us say you consider this as T1, this as T2, and this is corresponding to Cl1, this corresponding to Cl2. So what we did, we stopped the aeration, then we started and in any given 2 points, this let us say 5 and this is 5, this is 20, I have measured this saturation, but we need this Cl bar value as well. So it said when steady state is established, the dissolved oxygen concentration is 78%. The Cl bar is 78% air saturation. Then in separate experiment, the electrode response to a step change in oxygen tension did not vary with stirrer speed above 40 rpm. The probe response time under this condition was 2.8 seconds, and when KLa measurement was repeated using nitrogen spurging to deoxygenate the culture, the results for oxygen tension as a function of time were similar to those listed. Estimate the KLa. So it says you can use the either method, and whatever stirrer speed using, it is sufficient enough to remove the mass transfer resistance from the probe surface. So we will be applying the last expression which we discussed to measure the KLa for this dynamic for the gassing out method. So, at T1 5 second the Cl1 was 50% air saturation, at T2 20 second Cl2 was 66% air saturation, and at the steady state the air saturation was 78%. Now, we can directly use the formula KLA equals ln C bar is 78 minus Cl1 is 50 divided by C bar is 78 minus Cl2 is 66 divided by T2 minus T1. T2 is 20, T1 is 5. So, here we have directly used this oxygen saturation, air saturation. This can also be converted in terms of concentration, but this will be anyway cancelled out. In whatever factor we will use, it will be cancelled out here. So, in this way if you calculate, you will get the value of KLA as 0.056 second inverse. So, this is the KLA value. Now, if I calculate 1 upon KLA, I am getting 17.86 second. So, what it says, this probe response time is given as 2.8 second. It is much lesser than the 1 upon KLA. So, this satisfies the requirement for the measurement. So, this is the KLA value and the probe response time is good enough for this KLA measurement. Now, last method we will be discussing the sulfide oxidation method. So, this is a chemical reaction method. So, there will be reaction between sodium sulfide and oxygen, and in this way oxygen will be consumed. So, basically this chemical is simulating the oxygen uptake. So, we add the sodium sulfide and cobalt as a catalyst to the liquid, measure the oxygen uptake rate based on the sulfide oxidation. So, we can measure the concentration either the sulfide or the sulfate, and then from the calculate KLA from the reaction rate. So, here we do not require any live cells or the DO sensor, and this is suitable for high oxygen transfer systems, and as we are using the chemicals, so one need to be careful with the while handling the chemicals. So, the principle is very simple. The sodium sulfide is converted to sulfate using catalyst, copper or cobalt, and it combines this oxygen to convert to sulfate, and here the results vary with operating condition depending on the rate of oxygen transfer as well as the supply of oxygen. Then typically it can give a higher value of KLA as compared to the other method. In addition to this, when you are adding this salt, they also affect the bubble size due to change in the liquid coalescence property. So, this is not actually applied in the bioreactor, but in principle it can be applied for this high oxygen transfer systems. So, the concept is simple. We are indirectly measuring the oxygen uptake by measuring the concentration of either sodium sulfide or sodium sulfate. So, what is the application of KLA measurement? This is for the bioreactor design and operation, particularly for the aerobic fermentation, and when you are doing this scale up, there also this constant mass transfer requirement may be there, and it is important if you want to monitor the oxygen transfer in the cell culture system. There are certain challenges in measuring the KLA, the sensor calibration and the response time. The response time and need to be compared with the 1 upon KLA, and there can be change in the hydrodynamic conditions like flow rate, and fluid property that may affect the oxygen transfer and then measurement of KLa. In this chemical method, particularly this sulfide method, this chemical may interfere with the system, and in all the method we have made certain assumptions. So, one need to be careful about these assumptions for all three methods. So, with this I will stop here. That's what today we discussed. First, this how to measure dissolved oxygen, then what are three different methods to analyze the mass transfer coefficient KLa. The first one is oxygen balance method, very simple, measure the particularly pressure at the inlet and outlet and calculate the rate of oxygen transfer, then from there we calculate the KLa value. Second one is gassing out method. So, here we are purging with nitrogen gas to deoxygenate, then again you reoxygenate and calculate the KLa by measuring the concentration at any given two time points. And last one was the sulfide oxidation, where we need not have any DO probe, rather we have to chemically analyze the concentration of chemical, because it is uptaking the oxygen to convert sulfide to sulfate. So, I will stop here. Thank you. Thank you so much.